My name is Olena. I work at Aiven, and at Aiven we support and contribute a lot into open source technologies. We focus on data solutions. And today I wanted to talk about some of those solutions which are related to vector search. And we will see a lot of demos today, looking for some movies, searching for some puppies, exploring some recipes, and even using some power of a chatbot to make the agents to talk to each other and have long-term memories. But while doing that, our goal would be to look at building blocks of vector search and to talk about such things how KNN and what it is different from ANN, what different indexing strategies, what different distance metrics you have, and all those things. So stay here for the next 45 minutes and we'll cover multiple things, but before that, let's start with a simple question. What is vector search? Could you raise your hand if you actually already used vector search in the past? Oh, we have a bunch of hands. So for us to be on the same page for those people who are familiar with vector search and not, vector search is just an easy way to find related objects that have similar characteristics. And in vector search, we rely on a machine learning model to help us to detect those characteristics of different things, whether it is text, images, audio, or something else. And in a way, a machine learning model will distribute those objects which we analyze in a multidimensional space. Depending on the model, it can be anything like 512 dimensions, 300 something, over 1,000. So different models have different number of dimensions, and also they are not interchangeable. But because I'm not sure how about you, but I am not really good in thinking in thousands of dimensions. That's why I decided to present it in a simple two-dimensional way, how exactly vector search works. Each dimension actually would kind of respond to some characteristic of an object. We don't really know exactly what will be, which dimension is responsible to what. Machine learning models, they are quite complex inside, and sometimes during that building of machine learning model, they will have their own perception of different features. But the idea is when we analyze each of the things of entities we provide to that machine learning model, it will put it somewhere on that multidimensional space. And objects which have like more similar to each other will be positioned closer to each other, and those which have different characteristics from different areas, they will be farther away. So here I'm using some just images, but actually usually we are talking about some kind of textual data, some bigger things than just a picture of a dress. And once we have that stuff on our multidimensional space, we have the coordinates of those entities. And those coordinates we can work with, we can compare, and when we need, for example, to perform some kind of a search, similarity search, we use what is called a k-nearest neighbors algorithm. So this is an algorithm to find, for example, if you're searching for something, what is the nearest similar objects to it. And I think like the easiest way to perceive it is actually look at an example. And the first example I have is a recommendation system. It can be movies, it can be something else. Here we are just searching for some kind of like recommendations for what to watch. And there are different ways to build a recommendation system. Here today I'm talking about semantic search. So, and for semantic search, actually there are different ways to do semantic search as well. So we can use graph databases and other solutions. But for us, probably the most straightforward and accessible way is to rely on a vector search, where we delegate majority of the work to a model. And then the model will help us building that search. So, by the way, talking about semantic search, and talking about lexical search. So I guess right now we are using more and more semantic search, but still lexical search is very, very important. And in contrast to semantic search, a lexical search will look for literal matches of values. If you are looking for a puppy, it will only look by default for the puppy. If you want to make this connection that a puppy and a small dog or a pet is kind of similar and should retrieve those results as well, you will have to maintain some kind of synonyms dictionaries to connect those entities. And you can imagine that with the time, maintaining those dictionaries is actually quite a bit of an effort. So semantic search goes around it and tries to work with the meaning of the word by using different strategies. So for us, it will be vector search by using a model which actually knows that a puppy and a pet and small dogs are kind of like in the same area, and you might use those words interchangeably. So coming back to the recommendation system, let's imagine we have some kind of a data set. And then here's a data set with the movies, description of the movies. And what we do to work with vector search, there are like two major steps. So first of all, we need to process the data which we are going to search for. So we take the movie set, we take each individual movie, we use a model to convert that movie into a vector. So to put it into our multidimensional space. Here I'm using TensorFlow model. We are going to see today multiple different models which you can use. Again, like to mention this, they are not interchangeable. If you started using TensorFlow, it has 512 dimensions, and then for some reason you had access to another model, it has also 512 dimensions, you're like, why not to replace that one? You can't really do it because you are mixing some incompatible entities, so you stick to the same model. And with that model, you transform your data, and then you store it in some kind of a database. So here, there are a variety of options where exactly and how we can store it. But the important thing is that our database should be later able to work with vectors, to compare the vectors, so to perform that vector search. To start with, I'm using here Postgres because, actually, let's check this out. How many of you have worked with Postgres in the past? Could you raise your hand? So, like, majority of here in the room. So, if you will need to work with vector search, you actually can continue using your Postgres database, which you already know, which you worked for and have experience. The thing you will need to work with Postgres is actually PG vector extension, which you need to install. And then your Postgres is converted into a vector database. Amazing. So we process all the movies, and we store that in Postgres database, so all the vectors and corresponding information about the movie. This is step number one. Now we have a user. User comes there and types, I would like to see a movie with a lot of cute puppies. We take that phrase and we transform it to another vector. So now that vector we can compare to every other vector which we have in our database and find those nearest neighbors, which would be kind of a similarity search to find the recommendations which we have. So this is the whole idea and the whole flow of working with vector search in kind of a simplified fashion. This particular demo, and I will share at the end the links to the repositories with the code which you can steal or like get inspired by. So this one is built with JavaScript. You can actually use multiple different, I hope it's quite well visible, multiple different languages to work. I will use today JavaScript, Python, and Java a bit. So some languages have better options than others. JavaScript is, let's say, in minority. Like it's kind of like it doesn't really have so much good access for stuff, but still it's possible. So here, with JavaScript, we take the TensorFlow model and we use the libraries. They have the TFGS node library, which actually like adjusts the performance for the node. And then we convert an item like a movie description into a vector. And this is how the vector will look like. It will be just a long array with 512 numbers. So this is one of those. Of course, we want to process all the movies, and then we set up our connection to Postgres. We need to enable the extension vector, the PG vector extension. So if you are running locally your Postgres, then you will also have to install that extension. If you're using, for example, something like Aiven platform, we already have everything installed for you in advance, so you just enable it. And then once you have it, you have a new property. You have a property of a type vector. So in addition to all the usual stuff you have in Postgres, you now can store the vectors, and you will be working with vectors. So with that, once you have that table defined, we transform all the data, and we send all those records into a Postgres database. And later, we can search for those, for the items using the vector search, the comparison, relying on PG vector. And there are like different definitions of how you will be searching, because here we can use different distance metrics. So in any case, this symbol, and I'm very sorry if it's very dark, but the symbol actually, so I will show later other examples, but it's just to specify that we are going to use L2 distance. So, and we get 5 items from the 5 nearest vectors from the movie plots database. And then in the end, we can build a visual interface around it. So this is kind of like how we simply use k nearest neighbors. We process all the movies, we store the data, and then we search for the nearest neighbors there. And it will work pretty fast. However, like, for example, in that movie example, I had like 35,000 items. It's not a huge amount of data. So for your data set, you might have hundreds of thousands of items or even millions of records, and you still want to perform pretty fast the search. And usually, k nearest neighbor is kind of like, it's a brute force algorithm. We take the vector and we compare to everything else in the database. So this is not optimal, because it really depends how many items you have in the database. And the more you have, the slower potentially it will be with some kind of, the more items you will have, the more you will have to wait for the response. That's why usually we don't use KNN as it is. We add indexes. And for indexes, I mean, we do that for a variety of different other, so for all our databases, we technically use indexes to speed stuff up. So vector search is not an exception. That's what we actually call approximate nearest neighbor, is when we preprocess the data and we prepare it for the search request. So we shape it in a form where when the search request is coming, we know which data we need to analyze and which data will be kind of, we can omit and skip. And there are different indexes available. Here I want to talk about 2 indexes which I find they both exist in Postgres, in PG vector, and also they are kind of used in other solutions as well. So for us to understand how they might work, and also these 2 indexes, they are somewhat different from each other and has their pros and cons. So I think it's nice to understand how they will work and what options you have. So the first index which we have is called inverted file with flat compression. The name, to be honest, kind of sucks. But the idea is that we take all the data, all our data in multidimensional space, and we split it into clusters. For this, we find, first of all, some kind of a centroids. So we take the data, and we find kind of the groups of things we can combine together, and then we build the clusters around those centroids. And then later, when we need to search for something, what happens is that we are taking so we are having that vector for a lot of cute puppies, and we're like, okay, that particular vector, to which centroid it is closest to. And for example, it's like a green centroid. And then, okay, we will analyze only that particular chunk of our data, and we will omit all other clusters. So for this, you have different parameters. For example, you can specify how many clusters you want to have in your system, also how many those clusters you want to analyze when you are performing the search. Again, there are like pros and cons to balance the performance with the kind of the quality of the results we receive, so that we don't omit any of those closest neighbors. So this is option number one, just simply dividing the space into multiple clusters, or they call them lists. And this works pretty well. It's pretty easy to build this index. However, it has a couple of kind of things you need to be aware of. First of all, when we calculate those centroids, the positions and where we want to build our clusters around, it's good to have as much data already in the database as possible. So you don't want to start building this index till you have a big chunk of your data already. Also, the other issue is that what if you're constantly updating the records? You are removing some stuff, you add some stuff, and that's where you will have to re-index the data and recalculate those centroids so that you are not really missing those records. So this is kind of things to keep in mind. Lightweighted index, really good, but best if you don't really update data much. And also, when you index, you have a lot of data already. Next index. Next index actually has a way cooler name, hierarchical navigatable small worlds, and it actually creates a graph with multiple layers. And these layers are like zoom levels of the graph. So zooming out, you see less nodes, vectors, and less links. And zooming in, you see more and more nodes. So you can kind of find and navigate between those graphs. So this particular approach, it's actually kind of more expensive to build. However, if you're aiming at, like you need to improve performance significantly, this index will work faster. However, it will require more computational power to build. So this is like two indexes present in PG vector. Other databases, they will have those two indexes are quite popular, but you also have like other options. So whenever you have your data, most probably you will be using index. So check like what vector database you are using, which index it supports, and then see what pattern of data you have. For example, this graph database, it will be, graph index, it will be pretty good when you are updating the data. So you don't really need to re-index the data constantly. So if you, for example, update data and you actually want to create index even when you don't have many records, the graph index will be better. So this is indexes. When we're talking about indexes, we should also talk about a metric which we call recall in vector search. Recall is more or less is how close your results which you retrieved with vector search to the true nearest neighbors. So it may be that because you created that index, you miscalculated the centroids, you didn't re-index data on time, that what you retrieved is actually not really the real nearest neighbors, but some far away living vectors. So when we talk about recall equal to 1, it means that 100% of our results is the true nearest neighbors, and everything is less precise. So here, when we work with indexes, it's very it's natural that we will never get the recall value equal to 1, because we are doing some approximations, we are working with some heuristics, so it's mathematics. So we try to optimize and balance between performance and precision. So, and up to you, it will be like how much space you have for the performance and how much you need the precision. So it's a trade-off. Good. So enough for the theory for a moment. Let's move to the next example. And now I wanted to talk about this multimodal search. So in the movies, we were talking about text. But we have other type of data. We have images, we have sounds, we have videos. So because we rely on a model, if the model is capable of processing not only text, but processing, for example, images and giving the same kind of connected vectors, we can use model to make this link, for example, from text to an image. It can be whatever model is capable of perceiving. It can be also sounds, can be videos, which is kind of a bit more complex. But here I wanted to show an example how we can connect text with images. So, and here we rely on a model, clip model. This is also embedding model. By the way, this is maybe something I didn't mention. So for the vector search, we use embedding models, not large language models. We will talk about them a bit later. We'll use something a bit more straightforward. Our model just needs to take some source of information and return the vector. Otherwise, it's very stupid, not stupid, okay, they're smart, but not as smart as large language models stuff. So here, for example, to make the search for images, we can process a set of images which you have. For example, Unsplash has a big data set of images, and then we can take and transform each of those images into a vector. Next, we store that vector in another database, which is capable of working later with vectors and compare them to each other, and this is OpenSearch. I love OpenSearch. So OpenSearch has a lot of capability, again, to work with vectors and to compare, and has indexes and other features. So we transform and store the data there, and then when someone comes and searches for that image and types something there, we transform that request, again using the same model, but this model is capable of accepting text and images. And it will transform that text provided by the user who is searching for something into a single vector, and then we take and compare those vectors. So we do some kind of similar, for us it's all vectors, but it's just because the model can kind of make sense out of images, and the image of the dog and the word dog will be close enough for us to find those similarities. How many of you actually worked with OpenSearch? Okay, we have some hands, not as many as Postgres, but I think it's expected. So OpenSearch is an amazing database. It's a bit the difference maybe between Postgres and OpenSearch. In OpenSearch, we use it for logs, for metrics, and for other things. We don't usually modify data much after that. And Postgres is a OLTP database. So yeah, so with OpenSearch, you define that it's OpenSearch. I have some Python code here. Again, I will link to the code samples later. I must admit I'm a JavaScript developer, so my Python code and my Java code has a very strong JavaScript accent, but it's still a kind of working examples and stuff. So between OpenSearch, Postgres, and later we will see ClickHouse, there is one thing which is in common between actually whatever vector database you will take. There will be one thing. You need somehow to calculate the distance between those vectors and find what is closer and what is farther apart. And there are different stuff which you can use, different kind of metrics, or sometimes it's like mathematical. It's not really precise to use the word metric, but anyway. So we can use L2 distance or Euclidean distance. We can use L1 where you just need to make those corners. We can use L infinity, cosine similarity, inner product. So there are a different variety of things, and whenever you are diving in and you start building your own vector search, you're using vector search for your application. So I would recommend maybe to start with either cosine similarity or L2 distance. Every of those metrics has kind of like stuff which is specific to it. Normally we will have, if you're using an embedding model, you will have a normalized data set, so you don't really have like the vectors which are significantly bigger in distance. unless you're having some maybe a specific model, I don't know. But that's why both cosine similarity and L2 distance will be probably the better options. If those don't work fast enough, for example, L2 distance is like this Euclidean stuff, and you might remember from math from school, like it's like calculation of square root and a lot of different mathematics. So the more values you have, the more dimensions you have, it will be slower. So if that is kind of the limiting factor, you might want to try like L1 distance, less precise, but faster, again, finding the trade-off for that. Also, whatever model you will choose, you might also check if they have some recommendations and they actually tell you which metric is the best for it. Next thing for performance and otherwise what we can apply is, or actually sometimes we have to apply, is filtering, where you actually want to combine this structured search and vector search. For example, for our like movie data set, we maybe want to find the movies which are less than 2 hours, and then additionally for some specific topic. So here we have several options how we can do it. And I'll show this as an example of OpenSearch. You can do some kind of a pre-filtering. So pre-filtering would mean that first you will decrease the data set of the movies to only movies which last less than 2 hours. And then after that, you apply the vector search. Kind of a problem with that is that by selecting those values, you are going to lose indexes. So you kind of prepared, you shaped your data, you used those smart indexes to make the search faster, but here when you are filtering, you are decreasing the data set. So you either want to be quite creative with kind of having different indexes for different common filters, or in case you have a big data set, to make sure that that filter which you are applying is significantly reduces the data set, that you actually don't care about the index, you are gaining the performance just because you have less values to search later with vector search. So this is option number one. Option number two, post-filtering. It has its own disadvantages. This is like when we will first perform the vector search and say, okay, we want to find those movies again with cute puppies, because I guess majority of people like cute puppies. And then after that, we will decrease the data set and we will filter it by only the movies which are no longer than 2 hours. But that actually can result in a problem that we decrease the data set with vector search significantly, so that when you are performing the structured search, you will have 0 results, because there is none of the movies selected by vector search is longer than or shorter than 2 hours, whatever filter we had. So that's why post-filtering is kind of dangerous, because in the end you might be returning 0 results, when technically you could actually find something meaningful, maybe with less exciting puppies and dogs, but still it would be the length which is desired for the user. So that's why different vector databases, different solutions will have a other approach. So in OpenSearch, we call it efficient filtering. This is where actually the engine will decide what is better to apply: pre-filtering, post-filtering, and how to combine those results, so you don't really end up with those edge cases. So with OpenSearch, I would use that one. Also, re-ranking is another option to help with those things, to combine them together. I'll skip that. Then, what if you actually work not really with OLTP database, but you have a data warehouse? And here I wanted to show you an example with a data warehouse, which I truly love. It's a ClickHouse. So a ClickHouse is a columnar database. So instead of like with Postgres, we store data in rows, ClickHouse stores data in columns. So you have totally different approaches to indexing the data, to compressing the data. So it's super, super fast. The thing, usually you don't really use it, so actually you shouldn't really use it for OLTP. So if you have OLAP solutions, that's kind of perfect. And ClickHouse has a lot of different functions which you use for scientific computations. It has also approximation stuff. Like, it has a lot of things which people use for science, and it's used by a lot of different companies for that reason. And one of the things which comes out of the box with ClickHouse is also vector search. So here, in this particular example, I used a very small model, all mini, like so, it just has 384 dimensions, and then I store the data in ClickHouse, and then we can perform the similar search on that as well. ClickHouse is a bit different. I should have checked before the before this session if they have the indexes. It's super fast by default, so I think that with ClickHouse actually the indexing works quite differently. So maybe that's the reason. Well, they're like those indexes for approximation vector search was still in experimental mode. But with ClickHouse, they dynamically add so many stuff, so it probably will be also available sometime soon. But even without indexes, because the whole thing is structured very differently, I believe that ClickHouse will be quite fast solution for the vector search for big data which you need to store in data warehouses. So this is three different database solutions. Now, what I wanted to talk about also a bit related to the large language models. So we are using large language models in our life, and some people, and I'm pointing to myself, use them significantly more than I should probably have. But the large language models have their limitations. We need significant time to train the model, and also we often don't want to train it on some specific stuff, like for example, the user details. Like you don't want ChatGPT really know about your personal information. So, and then we have a different also other scenarios where, for example, ChatGPT or any other large language model will not really know about current traffic situation or like weather or stock markets from today, from this moment. But sometimes we want to provide the data as additional context. Same for user-specific details, same for any other stuff which large language model was not trained on. So for this, we are using what is called retrieval augmented generation, RAG. And it's actually just a complex phrase, like complex name for saying that we combine the results from kind of a vector search and provide those results to a large language model, to a chatbot, to generate us some stuff. So I have two different examples and demos to show with that. The first one would be if you have some kind of a product and you have your documentation and you want to have some kind of a generation of the answers to user questions dynamically. And for this, for example, I have this robot which I called Bleep Blop, and I have a stream of questions coming from the users, transformed by Apache Flink job to the answers, and we want to get those answers relying on some kind of a knowledge store, let's say your database. But how exactly we can do it? So we take, first of all, we are working again with vector search, but we take the knowledge store, your documentation, we chunk it into pieces, and we use an embedding model to store the data in a vector store. Here I used, for example, OpenSearch, but it can be ClickHouse, it can be Postgres, it can be any other database which supports vectors. So then, when we have a question from the user, we take that question and we actually calculate the vector for that question because it has kind of a context, and we see how it relates to all other topics which we cover in our vector store. One thing to mention here, when you are taking your database, you are chunking it to store in the vector store, you need to be quite careful. You actually don't want to do it like maybe paragraph by paragraph, because you're going to have a lot of nonsense, like kind of, for vector search, it's very important that we are describing different entities and they have kind of different locations, so we can find something meaningful. So usually what happens, we preprocess the data. Preprocess the data so that each of those chunks has encapsulated like information about some particular feature of our product. And then we find the relevant chunks, we take the text, so we found them by the vector, but of course for us it's important the text, and we add additional context to large language model. when searching for stuff. So I guess that will be very difficult to see. I will skip this. But so the idea is that then in the database, and this is OpenSearch dashboards, we have information about that feature of the from our documentation and the corresponding vector. And then later we find the relevant information for that. Another example, a similar one, how to use, again, vector search, but with combination with large language model. And this one is a bit kind of, I got inspired by a research paper, but then I was thinking, I'm not sure how many of you played Stardew Valley here. So I was like, it would be so amazing that the characters in Stardew Valley would be more dynamic. They could think about, and make the decisions, and they communicate between each other, and then this kind of influences their future lives. And actually, this is kind of similar to what the authors of the paper written by Stanford and Google have done. So they created some kind of a playground. And each agent in that playground has their own kind of the background story, and then using a large language model, we generate the next like kind of a movement or next phrase when they meet and talk to each other. But the issue which, or like the challenge which they had, and they were using admittedly ChatGPT 3.5, is a small size of a contextual window. So it's kind of to fit all the memories of an agent was pretty difficult, and kind of also to have it like, because there were like 20 or some number of those agents living in that village, and they were doing different things during the day, so it's a lot of different conversations they're having. And then the idea was that they would put some kind of an idea in the brain of one of the agents to organize a party, and then they see by the end of the day if the agent managed to organize all other villagers who didn't have that idea, and they would have some kind of party later during the day. And actually that's what happened. The whole paper is super amazing, super interesting. But coming back to vector search, and this is where we can have a long-term memory by summarizing the conversations of those agents, or like some memories, and then storing it in the vector database, because later we can find the relevant stuff again using vector search. And technically it actually also mimics quite well the real human behavior, because we don't remember all the details, or maybe I'm speaking for myself, but like my memory is really bad. But so like I would remember like a vague description, I was like meeting this person, and that's what we talked about. So by providing and using that kind of approach, we imitate more like a human similar behavior. So again, the code, I will add those links later. But the idea here, we, for example, have those agents. And the agent functionality, so I based it on Valky to use pops up to talk between the agents. So we have the kind of like each agent has the ears listening, and others can talk to that agent. And then I'm using additional pops up channel for reflections, because agents, they meet to each other, and then they have the conversation, but at some point of time they're like, okay, we are done, I have to go, I have some other things to do. So at that point of time we enter this kind of reflection mode, and we process the conversation and what was happening around, and store it in the memories for each of those agents. I'm using also Kafka topics, maybe not so relevant, just kind of for the ongoing memory. And later, when they meet again, to get relevant memories from the past for each actually piece of conversation, what we do, we go to the vector search. It's like, okay, so this is what is discussed right now. Do we have something relevant from the past conversations? Maybe they met like several times before, and like something like which can influence the current conclusion. And with that, they continue, they're building kind of their relationship. We also can use that information, for example, when they're meeting the second time, is like, okay, do I know this agent? Yes or no, based on the past fast conversations, and what exactly do I know so that I can start a conversation with some kind of idea. So this one I was using Kafka for ongoing memory, OpenSearch for long-term memory, and Valky for the PubSub communication. Yeah, and then later, for example, this one of the memories which I have. So for example, here I have a vector, and then like, for example, I had like Nick and Judy there, and Judy has some memory related to Nick, to conversation with Nick. Okay, last thing which I wanted to share, AI models. So a couple of things which you can start with. I mean, if you're already playing with vector search, I guess you actually already tried a number of different options. But if you are new to the world of vector search and augmented, so the RAG pattern, then for the large language model, Olema is very useful. So Olema is kind of this framework. It's used like you run a Docker container, you set the model you want to run there. Works very, very easily. Of course, like, I mean, it's also quite cheaper than using ChatGPT or other solutions. I also used it with GitHub code spaces. So kind of like those things, you can run it whenever you want and experiment with stuff. Then for RAG, also look into LangChain. Actually, so I use LangChain for all of those options, for JavaScript, Python, and Java. It helps you just to connect different like models and do some functionality. You can technically do those calls on your own, but LangChain hides a lot of complexity behind and offers you already existing interfaces for numerous different models. Then, if you are a Python developer, you have a lot of different options with Hugging Face. So I'm not a Python developer. However, I really enjoy like looking there, depending on the use case which you have, because you have a lot of different embedding models. And one thing important with embedding models, you want that the model, embedding model, was trained on the resources relevant to what you are using it for. So for example, like the model, like if it's a generic model, trained, for example, on the movies, and there are a lot of actually embedding models trained on the description of the movies. You don't want to use that model for kind of a vector search in some scientific literature, because it will just not know the context. So you need to make always sure. Then there are different sizes of the models. Sometimes the smaller size will be faster. You want to kind of play again like performance quality of the results. So Hugging Face is really amazing because you have a ton of different models, and then you can explore and see, even if you have some specific context, if there is an embedding model based on that. Yeah, TensorFlow, I'm not a big fan of TensorFlow, to be honest, but it's like for JavaScript, if I have to run stuff with Node, TensorFlow actually was pretty amazing. But Hugging Face models are better. With that, couple of links. So just to share a link, if you want to run, there's a free credits for the databases with Aiven. We have all of the databases which I mentioned and more. Then the link to the resources which, so the link, this is actually the demos and the like articles and videos. By the way, I also have a YouTube channel, and I also do some experiments there related to what I was talking today. And finally, we have our booth here, booth number 20. So later, I know that everyone is really in a hurry to get to lunch. We have lunch after this, right? So you can find me later there and drop by, and yeah, would be really great to talk. With this, thank you so much for coming to the session, and I hope you learned something new.